Thank you for having me. Today we're going to discuss why we should all be excited about AI, but also understand some of the limitations. In this case, I will use investment as a particular case, but as you will see, the results that I will introduce today are generalizable to many other areas. So let's start with the definition of the problem. The definition of the problem of investing can be stated as the following. We would like to figure out how we are going to assign some limited resources, in this case financial resources, in order to achieve a particular outcome. And what makes investing a very interesting problem is that this allocation decision is done under uncertainty. We do not know exactly what are going to be the outcomes. We understand that there are some patterns and relationships that we can use to guide this answer. However, this is done under uncertainty. And when you think about it, it is a fact of life that many of the decisions that we have to make are made under uncertainty. So what you can see here is the classical Markovich problem. We would like to minimize the variance of a portfolio subject to achieving a particular goal. The goal could be an expected return, or could be an exposure to a particular source of revenue, which we might call risk premium. And mathematically, this is a problem that was solved some 60, 70 years ago. Essentially, you just write your Lagrangian and you solve for first order conditions. You obtain this result. The important is this equation. Omega star is equal to B bar times this product of the inverse of the covariance matrix times beta, and then divided by that divisor. Now, what makes this expression interesting is that it requires knowledge of this B bar, which is our objective. Let's say that we would like to achieve an expected return of 10%. And there are some exposures that we are willing to take in order to do that. Now, the reason this is related to causality is the following. Where does this covariance matrix come from? These associations between returns. Typically, they come from a causal model, some structural model that is fit on the data that introduces some knowledge that we have about how these variables are interrelated. For those of you who are familiar with investing, this would be the typical Barra model. In a Barra model, you have some regressions that are measuring the relationships of some financial returns to some factor exposures: value, momentum, liquidity, quality, variance, and so on. Now, this is one way in which causality comes into play, and that is explained at the top equation, right? You would have some causal relationships that are estimated and utilized to estimate that covariance matrix. And causality comes in a second way as well, and it is when you define your target. Your target, for instance, would be to exploit a particular risk premium. Like, we would like to minimize variance while staying at a particular exposure to, let's say, the value factor, or the momentum factor, or the quality factor. So the statement I make is, in order to estimate this omega star, in order to solve this allocation, we need two unbiased estimations. Number one, the unbiased estimation at the top. This sigma is a function of this B times some factor covariance beta transposed, and these capital B's must be estimated unbiased. And the second requirement is that as well this small size beta, this lowercase beta, must also be estimated unbiased. So as you can see, in order to solve an asset allocation problem, the typical traditional classical investment problem, you need two types of separate unbiased estimations. And the problem is that in order to achieve these unbiased estimators, you need causal models. Unless you have a causal model, these estimates will be unbiased for two reasons. What is called confounder bias, and number two, what is collider bias. Confounder bias. Confounder bias appears when you have a causal structure like the one in this plot. You have a confounder Z, which influences X, the cause that we are trying to model, and the effect Y. So because the confounder bias appears because Z is not appearing, or it's not present in the estimator, and that biases the effect of X on Y. When you control for Z, which is done very easily when you just add Z as a regressor in your linear equation, then the estimates are unbiased and you can estimate beta correctly, the beta that we used in the second slide. However, when Z is not in your equation, then your beta is estimated with this red portion, gamma delta divided by 1 plus delta square. It will be biased. Now, how do we know whether we should introduce or not Z? This is where causality comes in. You need a theory. And absent that theory, you do not know that you need to introduce Z, and because you are not introducing Z in your regression, beta will be biased, and because beta will be biased, the sigma will be biased, the B bar will be biased, and your solution will not be optimal. So again, this is one clear mathematically provable way in which causality is a necessary condition for investment efficiency. But this is not all. There is a second reason why the capital B will be biased, and that's collider bias. Now, collider bias is even trickier. Collider bias occurs when Z is not a cause of X and Y, but the contrary. Z is an effect of X and Y. And why is this so tricky? Well, it is very tricky because when you leave Z alone, when Z is not part of your equation, then Z is not biased in your estimation. So you can obtain the correct small case beta unbiased when Z is excluded from your model. However, when you introduce Z, essentially when you mistake Z for a confounder, now the model will be biased, and sometimes so biased that even the sign of the beta will be reversed. You will end up buying stocks that you should be selling. You will end up selling stocks that you should be buying. So, as you can see, this makes colliders very dangerous, but there is a second reason why colliders are particularly, exceptionally dangerous, and it is that introducing a collider in your regression model will automatically increase the adjusted R-square. So essentially, whenever you are looking for explanatory variables, the typical canonical approach to model selection will lead you into incorporating colliders into your regression model. And in doing so, you will be biasing the estimation of beta. So let me repeat this. Suppose that you have some auto-ML approach. You're just trying many different things. You're adding all sorts of regressors. And your objective is to maximize predictability, right? Throughout today's presentations, that has always been the goal. We want to be as capable as possible of forecasting. However, in the presence of colliders, that guarantees that we will end up introducing colliders into the model, which will bias the estimates of beta, and therefore the investment decisions will be inefficient. They will be suboptimal. So confounders are problematic because when you forget adding them, the model will be biased, but at least the R-square will not be inflated, which means that at least it leaves you with the opportunity that eventually you will find a confounder and you will select the right model because that will increase the R-square. But colliders are particularly deceitful in the sense that as you are trying to maximize your predictive power, you will be encouraged to add this collider that will bias your estimation. And that's where we run into the problem of we need a different approach to model selection in finance, in investing, but I would say in general, in statistics. The way of selecting a model should not be guided by associational approaches that attempt to maximize explanatory power or achieve betas with a low p-value, etc. The choice of the model specification should be based on causal reasoning. And that's where the work of Professor Imbens and other leaders of causal inference, Miguel Hernan, both speakers today, is so helpful. Essentially, they warn us of the dangers of utilizing AutoML approaches that will lead us to biased solutions. So what can we do about it? Well, there are several things that we can do about this. Number one, we should stop using the kind of canonical approaches that are appearing on the textbooks. When you read some of the best-known textbooks in statistics and econometrics, you find statements like this. For instance, Greeny, 2012, page 136. The reduced precision of the estimates is the only downside of including irrelevant variables. Well, that is not true in the case of a collider. That's true in the case of a confounder, but we should not forget about colliders. And he also states, omitting variables from the equation seems generally to be the worst of the two errors, not in the presence of a collider. In the following page, 137, he recommends a general to simple approach where a researcher starts with a kitchen sink regression, which contains every variable that might conceivably be relevant. Well, colliders fit that description, and again, a collider will inflate your R-square, but it will bias your estimation. Oh, and there is a third problem with introducing a collider, which is very visible when you look at this graph. It's a cause of nothing. So we will end up with a regression model where we are inflating our R-square by adding something that has no relevance to anything. In the case of a confounder, at least we would be adding a cost to something, but Z has predictive power even though that power cannot be monetized because the effect has already occurred. So as you can see, there is the literature in finance in particular needs to become more aware of the issues created by colliders. And what can we do about it? Well, there are essentially two big solutions that we can pursue. Number one is what Miguel will explain in a moment. And one of his sentences that I've heard him say, and I find very powerful, is draw your assumptions before your conclusions. Here, he's playing with this dual meaning of the word draw. Draw in the sense of making a graph, but draw also in the sense of reaching a conclusion. Draw your assumptions before your conclusions. What it means is make a causal graph that describes the theory that you have in mind. this is the graph that justifies your model. Still, of course, the model will be wrong if your theory is wrong, but at least you are making all of these implicit assumptions explicit. So that's one very important, powerful advice. Before you go into estimating betas and running regression models or feeding machine learning algorithms, draw your assumptions before your conclusions. And as you can see, variables can play many different roles in a model. It could be a cause of X, or it could be a consequence of X. It could be a confounder, it could be a collider, it could be a mediator. It could be an independent variable, or it could be a cause of Y, or it could be a consequence of Y. There are all of these roles that a variable can play, and we cannot let AutoML approach that decision. That decision belongs to the realm of assumptions, and they need to be made explicit by the modeler. And then there is a second approach, which is causal discovery algorithms. There is some skepticism about these approaches. They are relatively new, and even though they are valuable and helpful, they are not a solution for every problem. Miguel, I'm sure, will also talk about that. In that sense, there are primarily three types of approaches: score-based algorithms, constraint-based methods, and functional causal models. On Thursday, we will make public the winners of Causal Lab tournament for causal discovery. And there you will see that we had an incredible number of participants who truly have presented breakthroughs. They have come up with very innovative approaches to try to discover what is this causal graph. The solution, the objective of this causal discovery algorithm is not really to find the causal graph, but to find the family of causal graphs that are consistent with the data. And some of these algorithms will leave some room for interpretation. So for instance, there will be some arrows where the algorithm will tell you, I don't know if this arrow is pointing to the right or to the left. The data doesn't allow you to derive that question. It could be that one is the cause of the other way around, but at least it will limit all of the millions of possible combinations to a few dozens or perhaps hundreds where the data is consistent with that causal structure. And once you do that, what you realize is that you end up being able to come up with models where the specification is not the result of some spurious association or some noise, but that it is founded on some understanding that humans as experimenters and subjects who are in contact with the data and the data generating process, they can insert that insight into the model specification in order to reduce the possibility of these biases. I produced this table where I try to make clear what is the ranking of empirical evidence in finance. Not all empirical evidence is equal. There is some evidence that one would consider relatively weak or subjective, for instance, an expert's opinion. Someone who says, well, I think that the stock market will go up by 10% next year. Perhaps, perhaps not. It's not much evidence unless the expert says, and this is why, right? And that's where we go back to the table. Then you have case studies. The last time that this happened, that occurred. Well, that's a case study. It's a bit anecdotal still. That would be, for instance, the case of broker reports or analysis. And then one step higher would be the traditional observational studies where someone runs some regressions. But again, the model specification will be left to some greedy algorithm that tries to maximize the adjusted R-square or some other objective function. And those are the bottom three types of empirical evidence. One notch higher is where we begin to introduce some causal insights. That would be in the case of simulated interventions, for instance, where we estimate a particular model based on some theory or hypothesis that we have in mind. And we make it clear these estimates are unbiased as long as this causal graph is close to what or to the data generating process. One step higher would be natural experiments. And there, of course, again, the work of Professor Imbens was truly, and is truly transformational and groundbreaking. That's the case where we try to utilize nature as the process for randomizing trials, right? Randomizing what is the control and what is the treatment. In the case of finance, for instance, would be the typical market maker reaction to random spikes in order flow imbalance, right? So where there's a random spike, and we can use this randomization of nature to try to understand what is the impact of market makers when this order imbalance is randomly increased. And then you have, as Professor Imbens explained this morning, really the most reliable way of trying to understand causality, and that's randomized control trials. That would be the gold standard. For instance, in the case of A/B tests, where you randomly send some orders to brokers, and and you measure what is the average outcome depending on one treatment or another. So this gives you an idea of what are the 6 levels of importance of the empirical evidence that is presented in finance. I have a few minutes left, but let me conclude here. The main takeaway from this presentation is that, of course, AI is something that is very helpful. We should all use it. We should all try to maximize our forecasting power, but always remember that even though you may have a model with a very high forecasting power, very likely that model will have biased estimates. And because these estimates will be biased, the investment decisions will be suboptimal. And they will be suboptimal for 2 reasons. Number one, because the covariance matrix will be biased as a result of these capital Bs that incorporate colliders or do not incorporate confounders. And number 2, because the small case beta will also be biased for the same reason. So these are 2 channels by which the absence of causality makes investment decisions inefficient. Thank you very much.
Thank you, Marcus. So I think we can take one question. Yes, Patrick.
Thank you. Wonderful presentation. I'm just really curious if, I guess a lot of the focus was on using relatively linear models and using R-squared as the kind of holy grail in terms of what we're trying to optimize. That if you have probabilistic models, if you have nonlinearity, and there's obviously situations where the R-squared is definitely not the right thing to optimize, does this problem become even more serious in terms of you optimizing?
Absolutely. And I referred to linear models in this case because that's the case of Barra, and that's the approach that is used, I would say, 99.9% of investment applications. But you're completely right. Not only we need to be aware of the issue of nonlinearity, but also threshold relations, right? There are situations where 2 variables are not associated until a particular threshold, and then they are associated. So these sort of discontinuities create a problem that will mean that very often these algorithms will bias estimations. The summary here is that it doesn't matter what is the functional form that connects x and y, is the fact that these two variables are connected. It can be in a linear function or a nonlinear function or a discontinuous function. It can be any sort of functional form, but the key concept here is that the presence of colliders introduces a channel for maximizing your objective function in a way that it biases the estimations, and by biasing the estimation, the portfolio will not be optimal.
Thank you, Marcus.
Thanks.